We want to now conclude the proof of Tychonoff's theorem. So let me remind you where we'd got to last time. So we'd had this lemma 2.6 talking about maximal FIP collections, or FIP families, and which turned out to be the same things as what other people called ultrafilters. Since we haven't gone through the usual definition of ultrafilters, we had to mention some of the properties that these things have got, some of which are actually part of the standard definition of ultrafilter, but because we defined an ultrafilter to be a maximal FIP collection, a maximal collection of subsets with finite intersection property, so we actually had to include that as part of our lemma. So the first thing is, if you've got any FIP collection, any collection with the finite intersection property, then it is contained in some maximal FIP collection. And such a maximal FIP collection is an ultrafilter. And that's what we called ultrafilters in this module. And of course, the empty set isn't in. Finite intersections of things in your ultrafilter are still in your ultrafilter. So ultrafilters are closed under the operation of taking finite intersections. If you've got some set in your ultrafilter and then some other set that contains that as a subset, then the bigger set has to be in the ultrafilter as well, using maximality. And then a very useful fact that if you found some subset of X which meets every single element of the ultrafilter in a non-empty way, then that set has to already be in the ultrafilter. And we proved the existence of these ultrafilters using Zorn's lemma. Oh, a little note in there. I said let C be a chain. This is a common oversight in the literature, and I've made the same oversight again. The empty chain is usually trivial, but only provided you know your partially ordered set is non-empty. So the empty chain is always handled by taking any element of your partially ordered set. But that only works if you've got a partially ordered set that's non-empty. We did check our partially ordered set was non-empty, so that was okay. I should have said let C be a non-empty chain, and because otherwise the union of a whole load of FIP families in the empty chain, would be the empty set, which wouldn't have the properties we wanted, because we wanted an FIP family including, which included all the sets in our smaller FIP collection. So you shouldn't take the empty chain there. Okay, so then we started to prove Tychonoff's theorem, and I started with the observation, if you take some FIP family on X, what you want is to show the intersection of the closures is non-empty. So if you make your collection bigger and still show the intersection of the closures is non-empty, then you've done even better. Because if you intersect more sets, you tend to get a set that's smaller. And whenever we've got a collection, we want to show the intersection of the closures is non-empty. We'll do it by finding a point so that every open neighbourhood of the point has non-empty intersection with every set in your collection. So we apply our lemma and say you can boost your original FIP collection up to an ultrafilter by adding in some more sets if necessary. And now we'll show that the intersection of this bigger collection of closures is non-empty, which will show that the intersection of smaller collection of closures is non-empty as well. So far we haven't used the fact that we're in the product space. And that's our next task. So for each I in I, consider the images Px of A, Pi of A where A is in the your ultrafilter. So this is a collection of subsets of xi. So let's call this Fi. So this is a set of subsets of xi. So you look at all the I-coordinate projections of elements of your ultrafilter. Well, because the ultrafilter has the finite intersection property, and because when you form a projection of one of these non-empty sets, you must get a non-empty set. The coordinate projections can never map. You can never map using a function a non-empty set to an empty set. That wouldn't make sense. So you can quite quickly show. Actually, there's a containment thing. Remember, the image of an intersection is not necessarily the same thing as the intersection of the images, but you do get an inclusion one way around. So let's have a look at that. Suppose you have E1, E2, and so on up to En are in Fi, then Ek is equal to Pi of Ak, say. For some Ak in the ultrafilter. But then the intersection of, I claim that the intersection from k equals 1 to n of the Ek is non-empty because it has in it P of x for all x in the intersection from k equals 1 to n of Ak, which is non-empty. The image of the intersection is a subset of the intersection of the images, but it doesn't have to be equal to it. You can have two disjoint sets whose intersection is empty, but where the images are both the same, and so the intersection of the images can be strictly bigger. It can't get smaller, so it's not going to be empty. So each Fi is an FIP family, an FIP family, or collection, on its relevant space. But they are compact. The Xi's are compact. There exists an Xi. This is axiom of choice again. We can find an Xi in the intersection over E and Fi of the E closures there. Which is equal to the intersection over A in F of Pi of A all closed. And now we use those xi to make a point x in the product. So we know the intersection of those closures is non-empty because that's true for any FIP family in a compact space like xi. Now we put all the xi's together to make a point x. So set x equals xi in the product over I and I of xi with xi as above. So you've made it up out of coordinates, each of which is in its own separate intersection of closures. Now, it's not at all obvious that x is where we want it to be. And that's what we have to prove. And that's using the properties of ultrafilters. So we show that x is in the intersection over all A in the ultrafilter F of A closure. It's plausible because its coordinates are in the right sort of place. Its coordinates, each xi, is in the right sort of intersection, and so it seems hopeful. So let U be an open neighbourhood of X. Notice my abbreviation for neighbourhood here. NHD is a nice abbreviation for neighbourhood. What have I got to prove? If I want to show that X is in the intersection of all these closures, what do I have to prove about U? I'm sorry? That's right, it must meet all of them. So for X to be the intersection of the closures, U must actually meet all of the sets A. Actually, though, bearing in mind this is an ultrafilter, what will that tell you about U? U would actually have to be in the ultrafilter if it's going to meet them all. So in fact, we're going to be proving that U is actually in the ultrafilter. But I mean, just at the same time. What we'll do is we'll show that U is a superset of a finite intersection of sets in the ultrafilter. We know that ultrafilters are closed under finite intersection. And we know that, so if we can find finitely many sets in the ultrafilter whose intersection is a subset of U, we'll be in good shape. But what's a base for the product topology? What's the standard base for the product topology? What did we call our basic open sets?
Finite number of open neighborhoods out of some of the xi's, and the rest of them have to be the whole of the x.
That's right. So, and one way of saying that it was that sort of this product where most of them had to be the whole thing and finitely many were specified, is it's a finite intersection of pre-images of open sets from the individual spaces. So if you think about what we're trying to do with the ultrafilter, I'm going to try and show that U contains some finite intersection of things that we know are in the ultrafilter. What's going to happen is that we'll use the definition, and now we have to somewhere, use the definition of what the product topology is. And finite intersections are crucial here, and you'll begin to see why things work for this product topology and wouldn't work for the box topology, where you could have sort of intersections of uncountably many pre-images of open sets and you'd be in a mess. Okay, so then by the definition of the product topology, there must be, well, there's got to be a basic open set containing X and containing U. Okay, so there is a basic open set with X in V and a subset of U, where it's a basic open set. V has the form intersection from k equals 1 to n, a pre-image under ik of subset uk, where I1, I2, and so on up to In are in I, your indexing set. I1 up to In are in I, and UK is an open set in X sub I sub k. So that's your typical basic open set. And you've got to be able to find some basic open set round X inside U. And that's going to be enough for us, because we're going to show that V... can you see what I've done wrong? I've missed the... It's supposed to be a pre-image, right? So it's a finite intersection of pre-images of open sets using the coordinate projections. So I'm going to show that U is in the ultrafilter, which will make it meet everything in the ultrafilter. We'll do that by showing V is in the ultrafilter, because V is a subset of U. And ultrafilters include everything that's bigger than something already in. We'll show V is in by the fact that each of these PIK inverses of UKs are in. And that will follow from the choice of the X sub I sub k. So let's see how that works. So for any k in 1, 2 up to n, note that xik is in the intersection of the closures, the intersection over A in the ultrafilter of the closures of the set PIK of A. Notice that since X is in the pre-images under PIK minus 1 of UK, that tells you that PIK of X is in UK. So since X is in PIK to the minus 1 of UK, we have XIK must be in UK. That's what it tells you. Your IK coordinate must be in the relevant set. So since UK is open, U intersection PIK of A is not empty for all A in F. If you need intersection of these closures, that means that every open neighbourhood meets every one of those. UK meets PIK of A for every A in the ultrafilter. But now, a tiny little bit of thought. When you look at the pre-images, you'll see that that means the pre-image of the UK must meet A. I'll leave it to you to check that one. It's, as usual, an inclusion one way round. So PIK to minus 1 of UK intersection A is also non-empty for all A in the ultrafilter. One way to see that is you take a point that's in UK intersection PIK of A, then it must be PIK of something that's in A, and that thing that it's PIK of is in PIK to the minus 1 of UK intersected with A. So it's that way round. So I'll let you check that. Right, so now we've arrived at this pre-image meets A for every A in the ultrafilter. But it's an ultrafilter, so what's the conclusion? If something meets everything in the ultrafilter, what could you say about it? So the property of ultrafilters, that if you have a set that meets everything in the ultrafilter, then it has to already be in the ultrafilter. Otherwise, you could throw it in to make the FIP collection bigger. So this is all by different bits of lemma 2.6. So PIK to minus 1 of UK is actually already in F. This is true for 1 small equal to k small equal to n. So, since ultrafilters are closed under finite intersection, the intersection of those pre-images will be in F as well. That's V. And since V is a subset of U, U is in F as well. So I'll note this is using properties of ultrafilters that in lemma 2.6. Repeatedly. And in particular, U intersection A is non-empty for all A in the ultrafilter. And since that was true for that one, there was a smaller collection S. We also have what we wanted in the first place, that U intersection A is non-empty for all A in the smaller collection as well. And we finally proved it. Now, that, as I say, is the hardest proof that we will meet in this module. So it's possible you have some questions about it. Or you might have some questions later about it. Does anyone have any questions about that right now? If not, then feel free to contact me another time with any questions you've got about it. And what I'll do is I'll stop the recording there because we'll be moving on now to section 3.1.